Good. Shaker, thank you very much. Okay, people, let's get started. Okay, so we'll be discussing the elements of the immune system. And what's going to, you'll notice that Dr. Tewari, Dr. Hamby, and I will discuss actually the same interaction, but from different angles. And this will give you a good idea, for example, of how a dendritic cell interacts with a T cell, interacts with a B cell. This all has to do with regulation, okay? And there's a lot of planned redundancies. Dr. Laria will speak about the lymphoid tissues, which is great, and Dr. Maresh will speak about the inflammation and repair. Okay, so when you think about the immune system, what do you think about? You're thinking about, hey, it's going to protect us from all these bacteria, viruses, and fungi and parasites. Cool, it does that, okay? But the truth is, what it's doing 24/7 is actually protecting us from our normal, microbiota, protect us from the normal flora, because there's a constant inside-outside battle. Bacteria that we have in our GI tract always want to get into our tissue. Same thing in the mouth. We have millions and millions of bacteria a day getting out of our mouth into our tissue, but it's our immune system that actually protects us. Kids that are immunodeficient, they're not getting Ebola and Zika virus and all this. These kids are actually suffering from E. coli, from all the commensal bacteria which we all have. Okay, but our immune system keeps us in check. And also the microbiota actually shapes the immune system and the immune response, okay? It induces tolerance. You think about it. Kid comes out, kid is sterile, kid's just born, right? Next thing you know, he's got millions of bacteria coming from the mother, coming from all over the place. Okay, now he got the GI tract, which was sterile. Now it's being colonized by bacteria. Why is there not a huge inflammatory response, right? And the truth is because the microbiota that the mother had produced products which told the GI tract, hey, chill out, good guys are coming, and actually it induces tolerance. So it's actually, there's a beautiful system, okay? The microbiota of the mother affects the fetus and so on and so forth. Now, let's speak about the immune response, okay? The immune response, okay, that's supposed to be protecting us from all of these pathogens, okay? There are 3 R's. There's the recognition, okay, and it's recognition of what's foreign, but it's not really what's foreign, it's really what's dangerous. What you ate for lunch today is foreign. I mean, why don't you mount a huge immune response when you have a tuna fish sandwich, okay? But because your immune response does not respond, when it's regulated, does not respond to what's foreign. It responds to what's dangerous, okay? Next, and how does it, know what's foreign and what's dangerous? Well, it has receptors. There are some receptors we'll discuss that are very broadly specific. They'll see all RNA viruses. They'll see all, gram-positive bacteria, all gram-negative bacteria. And there are some narrowly specific. Narrowly specific means it's only going to see influenza from this year, not last year. It's going to see only one type of a SARS-CoV-2 a variant and not another one, okay? And we'll be discussing these. The biggest one is regulation. You kind of notice that there are a bunch of exclamation points. Regulation is the most important thing. The immune response can be extremely strong, and if it's not regulated, you are going to be the target, okay? Not the bacterium, and that's extremely important, okay? There are many layers of regulation, so we respond to what's dangerous, not the tuna sandwich or the manicotti or whatever you ate for lunch, okay? It's a combination of soluble factors and cell-cell interactions that have to do with this regulation. They all have clinical and therapeutic relevance. If you know how something works, now you could use it. Do I want to upregulate this? Do I want to amplify this reaction? Or do I want to decrease this reaction? And that's all being done right now. What we know about the immune response now is in the clinic tomorrow. And this is really, really exciting. The immune response should be hard to get started. By hard to get started, it should be hard because we're surrounded by foreign objects that we don't want to respond to. And it should be easy to stop. So when you do respond to something, when you get influenza this year, you're not responding to it for 10 years to come. It's over a few weeks later. That's all regulation. When to start, when to stop. Okay? And this regulation protects us against autoimmunity. I said, you're going to be the target. Against hypersensitivity, okay? Your lunch is going to be the target. The cytokine storm that Dr. Bakshi spoke about. COVID pathology is mostly immunological. And so much, this whole inflammation and repair and so much of our pathology and illness is due to a dysregulated immune system. Okay, now, there's two different types of the immune system. There's the innate immune system, which is the first line of defense, and that's the first 4 days of infection, okay? It pre-exists or is very rapidly mobilized. It's ready to do battle. It's in your skin, it's in your respiratory tract now. For the virus that you're going to see a month from now, it's already there. You have macrophage skin that have been there from the day you were born, ready and waiting and ready, willing, and able to do a good job fighting for you. Okay, the goal is of the innate immune system is to eradicate infection or at least contain it until the adaptive immune response comes to play. Does a hell of a good job. 90% of our infections are taken care of by the innate immune system. It does not improve, okay, or get better with repeated exposure. You know, this whole thing about I have immunological memory, I'm immune to something, nothing to do with the innate immune system. It's all, that's the adaptive immune system. Innate immunity today, you see the same virus 2 months from now or 2 years from now, same immune response, okay? And what's involved in the innate immune response? Phagocytes like macrophages, neutrophils, dendritic cells. You have cytotoxic natural killer cells, okay? And these are against virus-infected or cells that are stressed, or like cancer cells or other cells like that, okay? By the way, all of these things are going to be discussed again. This is just a good overview, okay? There are soluble factors like complement and serum factors, okay? Cytokines and interferons, which really get messed up with COVID-19, okay? What Dr. Bakshi spoke about and which I'm going to be mentioning today. Dysregulation of the immune system is what pathogens want to do. Because if they can dysregulate the immune response, we can't respond against them. This is really, it's us against them, okay? You know, we're smart, but they got more of them because they just keep multiplying millions at a time. Just evolutionarily, we keep fighting each other. We're still here, they're still here, and we're going to keep it going, okay? That's why we all have jobs. Okay, next. And these receptors recognize molecules that are common to whole classes of microorganisms. Remember I said there are receptors that see large groups of bacteria, and there are some that only see one variant, okay? The innate immune system has receptors that will see, for example, a cell wall component, which is going to be found on 99% of all bacteria. Okay, and that's cool. You know, and not molecules that are specific to just one species of bacterium. So there were just a couple of hundred receptors, and that's on the high side. Okay. Importantly, it sets up the inflammatory process. Okay, that's regulation. To get an adaptive immune response, you need an inflammatory response. That inflammation is telling you, hey, there's something dangerous, okay? So that's important. It sets up the inflammatory process, and it's when it's regulated, it's great. When it's not regulated, you get cardiovascular disease, COVID, okay, cancer. And then what it also does is it sets up the adaptive immune response. It's also regulation. Everything starts with the innate, at least initially, and then all of a sudden, then the adaptive can take over. The adaptive immune system is what you guys know, okay? It's called adaptive because it adapts to the infecting pathogen. It's an adaptive immune response to this year's influenza, to RSV, to this strain of COVID, okay? It has antibodies and it has T cells, only found in vertebrates. Receptors are usually specific to one pathogen, so that they're narrowly specific. You have billions of them. You make antibodies to things that don't even exist. Okay, I mean, if a rocket comes back from Mars with a brand new thing, we have antibodies against it. I know it sounds crazy, and it is, but it's an incredible system. Dr. Tewari and Dr. Hamby will speak about how this diversity is generated. Okay, and when you find this pathogen coming from Mars, you're going to amplify the numbers. So you have lots of different specificities, small numbers of them, of each one. But then when you need it, you amplify it, okay? And it also uses the cells and the soluble factors of the innate immune system. And it relies on the innate immune system for for stimulation, okay? And that's the regulation. And it gets better with repeated exposure to the pathogen. That's immunological memory, okay? So with the adaptive immune system, we get the we get protection, we get whether it's natural or artificial immunization, which is vaccination. And that's the ability to fight off an infection after the first exposure, okay? First exposure, primary adaptive immune response is slow. Remember, the innate immune system comes up first. The adaptive immune system is slow. If we had to wait for the adaptive immune system to come up, we wouldn't be sitting here talking about things, okay? It's a big problem. It takes a while to come up, and I'll show you slides on that later. Okay, primary immune response is slow and weak. We get sick, and hopefully we recover, okay? What we try to do is, with vaccination, we try and make believe that we were sick and we get exposed to it, okay? But what happens is whether we're exposed to it and we get sick and recover, or we're vaccinated, okay, we remember the pathogens that we've been exposed to. We get an upgraded immune response against that pathogen. It's qualitatively and quantitatively different. And Dr. Tewari and Dr. Hamby will speak about that. And it's faster. What normally can take 12 days is going to take 2 days or 3 days. So when you're exposed to the pathogen again, you don't even know you were sick. Yes, it came in you. Yes, it replicated a little bit, but boom, your hyped up immune response was able to get rid of it. So you can resist symptomatic or severe infection. So what we have is with an innate and the adaptive immune response. One thing is we have regulation going back and forth. It's bidirectional. Okay, it's a rapid response is within hours. Okay, the adaptive is slow. It's after day 4 as you first start noticing anything. Fixed receptors, and these are variable. Okay, and Dr. Hamby and Dr. Tewari will discuss this. Limited number of specificities. I said a few hundred. You're going to get billions of them. I mean, 10 to the 9. Yeah, so it's 10 to the 9, 10 to the 10, about 10 billion or so. Okay, constant during the course of an immune response. This gets better with time, and they do work together. Now, let's get a couple of terms straight. An antigen is a molecule that will bind to an antibody or an immunoglobulin. Now, an immunogen is an antigen that can stimulate an immune response, right? So like I said, cucumbers are antigens, they're not immunogens because we don't respond to it, okay? Now, so an immunogen has an immune response generation capability. Small peptides, haptens are antigens, not immunogens, okay? So when things are regulated, when there's good regulation, most of these items are antigens, but they're not immunogens, okay? If things get messed up with regulation, then you got a problem, okay? Then antigens become immunogens, and we begin to make antibodies. That's why we have allergies, autoimmunity, and other issues. There's a term called a determinant or an epitope, and that's what an antibody is actually binding to. So if this was a spike protein, okay, and it was thousands, hundreds and hundreds of amino acids long, the antibody is only binding to about 6 amino acids of it. That's called a determinant or an epitope. So if you're going to make a vaccine, you don't need something that's 200-300 amino acids long or 1,000 amino acids long. You need something that, if you can maintain the conformation and the structure, you just need something that's about 6, okay? And different antibodies will be binding to different portions of it. So what we're really interested in is what is the epitope, okay, that an antibody is binding to? What is the epitope on the spike protein that an antibody has to bind to that will neutralize the virus, okay? And this is a linear epitope or determinant, and this is a conformational one, okay? And that's important. When you know what you're looking for, then you're going to design the right vaccines. Yes. Yes, what's going to happen is you're going to make antibodies to whatever is going to be different, right? But given that an immune response already started, now things that were previously just antigenic, now they're actually immunogenic, right? So you make antibodies to everything. So you're going to have another antibody, and then this is going to be the determinant. So you can have loads and loads of determinants. But let's say you're working for a drug company and you're making and you're designing an antibody. This is what we did initially with the coronavirus. We had monoclonal antibodies. And from the first patient, Eli Lilly, they had over 400 different antibodies that they were looking at. A lot of them bound but they had no effect at all on neutralization. You need something that's going to bind to the right portion of the molecule. So it's very smart to know the science behind it so that what you're learning here makes its way into the clinic. And you saw how fast things went from the laboratory to the clinic. It's really, really cool with COVID. Dysregulation, what I'm complaining about all the time. Okay, and they're evolutionarily flexible. They respond to the selective pressure of the immune system, and so does cancer also. So, for example, SARS-CoV-2 totally subverts the immune system. It totally messes it up, okay? And cancer also has ways to subvert the immune response. Yeah. You can have repeats. That's one of the keys to autoimmunity. So, for example, a lot of spikes in autoimmunity. So a person will have an autoimmune disorder, but then all of a sudden it gets worse, right? They may have had an infection with a pathogen that had an epitope that was very, very similar to your self molecule. And that's a very, very good point, okay? So for example, the answer is yes. They're all over the place, okay? But that's why you need regulation, and that's why you should not be mounting the immune response against yourself. Okay, the dysregulation may occur because of a virus infection or bacterial infection, and we're going to cover that. Which pathogens and diseases and infections are associated with which autoimmune diseases. This is really cool stuff. Okay, now, and in addition to pathogens messing us around, we also have immunodeficiency. Carl Hamby will be, discussing, like, for example, the genetic immunodeficiencies, and we're going to have a couple of sessions on immunodeficiency. There's also acquired. So one is genetic and one is acquired. There's collateral damage, which Dr. Bakshi was talking about right now. You get global stimulation of the immune response. You get massive cytokine release called the cytokine storm. You get tissue damage and death. So if you make too much of a good thing is not a good thing. End of discussion. Allergy. Okay, and hypersensitivity, we make inappropriate immune responses. Dr. Hamby is going to discuss this, whether it's food or to things like pollen or to bee stings or peanuts, you can get tissue damage and death. Okay, an allergy is not just an annoyance, it's a life and death situation. Autoimmune disease, where we actually make the immune response against ourselves. Okay, transplant rejection is not really it's not really self. Okay, but once you put it into, as a physician, once you put it into someone, you want it to be recognized itself. So there are ways that you can dampen the immune response. Remember, if you know how things work, you know what the factors are, the regulatory factors, you can shut things down, and we'll have a whole lecture on that. So you really need a regulation. Okay. So we started off talking about the factors of the immune system, clearing bacterial, viruses, fungus and everything. But as clinicians, what are you going to spend your time with? Allergies, contact dermatitis, celiac disease, inflammatory diseases such as cardiovascular cancer, or the issues with inflammation and repair, autoimmune diseases, tissue rejection. And this is rejection of transplanted tissue, what's referred to here. Graft versus host is when you put a bone marrow transplant into someone and the bone marrow begins to reject the person that it's in. It sounds freaky, but that's a major problem. It happens in almost anyone who gets a bone marrow transplant, okay? That the bone marrow begins to reject the person, okay? And we'll discuss that later on. So essentially, we see immunology. You need to know all this, okay? Because once you know the regulation, if you need to stimulate an immune response against a pathogen, we can make better vaccines. And when we discuss the vaccines later, you'll see that's exactly what they did with the messenger RNA vaccines, okay? And the vaccines can be prophylactic. You get the vaccine before you get the disease, or immunotherapeutic. When you already have the disease, you may be able to stimulate the immune response to it. So it's immunotherapeutic. There are things called adjuvants, which kickstart an immune response, which can turn an antigen into an immunogen. So you have something that may be totally useless as a vaccine, but if you give you it's going to work. Okay, Dr. Tewari is going to speak about suppressing negative regulators. These are called checkpoint molecules. Remember I said that, hey, it's important to stop an immune response when you're finished with it? Cancer cells know that. and they put up checkpoint molecules and they stop your immune response against it. So do bacteria. It's a crazy thing. You know, unless you study it, you never believe that it happens. But this is what they do. Okay, and then right now, Dr. Tawari will speak about the checkpoint inhibitor therapy. It's first-line treatment against melanoma. It's not this kind of thing that you do, you know, later on in treatment. It's the first thing that you do. Also, if you know the immune response, you know, and the regulation, not just stimulating, but you want to suppress immune responses. You want to suppress autoimmune responses. You want to suppress transplant responses, allergic responses, and cytokine storm. And this is all being done right now. So personalized medicine is just really something that we're all going to be involved with now. So now what I have is I have an animation. By the way, these animations are on Leo. You can get them, but let's listen to this. I have to. 1 second.
An immune response involves events that unfold both locally at the site of an infection and at more distant sites, such as nearby lymph nodes. We can see the integration of the different parts of the immune response if we follow the course of a typical infection. Most pathogens are kept outside of the body by epithelial barriers, such as the epidermis, and are crossed only when there is an injury or tissue damage. After an injury, bacteria cross the epidermis and establish an infection in the underlying tissue. Phagocytic cells in the tissues, such as macrophages and neutrophils, engulf the pathogen. Dendritic cells are also phagocytic and are activated by binding pathogens to leave the site of infection and migrate to a lymph node. The migrating dendritic cells enter the lymphatic vessels and are collected in a draining lymph node. In the lymph node, T cells are activated by antigen presented by the dendritic cells, and in turn activate B cells to secrete antibody. Effector T cells and antibody molecules return to the circulation. They leave the circulation again at the site of infection, where inflammatory mediators have induced changes in the blood vessel endothelium. CD4 T cells activate macrophages to become more cytotoxic, while antibody recruits complement to lyse bacteria directly and to opsonize them, enhancing their uptake by phagocytes. In the case of a viral infection, activated CD8 T cells would kill any infected cells present. An immune response.
Okay, good. So let's get this going. Okay, so this is an overview of what you just saw. Here we're going to be, in the next hour, we'll be discussing the innate immune system. Okay, here you had the dendritic cell and the macrophage. Here you have a neutrophil coming in after it's been induced, and then you're going to get the adaptive immune response. An important point is that the innate immune response is everywhere. Okay, and it's the same. The macrophage from anywhere in your skin is going to have the same receptors on it. The adaptive immune cells of a particular type all have different receptors. So in other words, every B cell has a different antibody on it. Every T cell will have a different T cell receptor on it. Okay, and the key is that you can't have all of the immune system everywhere in the body. So for example, if you, in this portion, in this square millimeter, if you had to get all of the adaptive immune system, you had to get billions of B cells there, it would be crazy. So the innate immune system works everywhere, but you have particular places like the lymph nodes and the spleens, which Dr. Hamby, Dr. Tawari, and Dr. Luria are going to be discussing. This is where the adaptive immune system goes. So the T and B cells with all of their billions of different receptors, they will be meeting the antigen here. So the antigen will go from the area of for example, here the skin, the antigen and the activated dendritic cell will come here, and then the T and B cells will be going through here. And we're going to be discussing this right now, in a minute or two. Here are the cells of the immune system. Okay, when we look at the common myeloid precursor, we have allergies. We have allergies which are caused by the mast cells. Okay, we have dendritic cells and macrophages, which are phagocytic and regulatory, because they will direct T cell differentiation. You have the granulocytes, which are the neutrophils, eosinophils, and basophils, and we'll bring all these. When we shift over to the lymphoid cells, Well, these are the natural killer cells, which are part of the innate immune system, which are against virus-infected cells. These innate lymphoid cells are their importance is just beginning to be realized now. And Parham has a whole section on it, but don't sweat it, okay? Because we're not going to cover it much, okay? But eventually it will be, we're going to know more about them, but they're actually very exciting. You also have the CD8 cells. These are effector cells. They kill virus-infected cells. You have the T cells. That's the different CD4 T cells. These are different subtypes. And there's also T follicular helper cell, which Dr. Hamby will discuss. These are all regulatory. This is effector. This is regulatory. And here's the B cell, which gives you a plasma cell. And this is going to be making antibodies. We'll be covering all of these again. Now, the primary lymphoid organs. This is where lymphocytes mature and they're educated. Right? Mature means from being a regular bone marrow cell, making their way and going along the lineage that we just saw, and also learning self from non-self. These are the first stages in preventing autoimmunity. So in the primary organs, you have the B cells being made in the bone marrow. Some bone marrow cells make their way to the thymus, and then they become T cells. They become CD4 or CD8 cells, but which CD4 cell they make actually depends later on into where they go and what they encounter. So this is where lymphocytes mature and are educated. In the secondary organs is where the immune system is exposed to pathogens, okay? We're talking about the adenoids, the tonsils, the lymph nodes, the spleen, the Peyer's patches. This is where you're going to get an immune response, okay? When the cells come out of the B cell, the bone marrow or the thymus, they are naive. They're mature but naive, meaning they've never seen antigen before. When they come into here, when they come into the secondary organs, they're willing to go a little bit more maturity, maturation, and then they're also going to be exposed to pathogens. Okay, good. Now, as we saw in the animation, you'll have an infection over here. Here's a dendritic cell. There's macrophages. You're going to have antigen. A lot of the innate immune system will be taking care of business here, but you're going to then have macrophages and dendritic cells making their way through the lymphatics into the lymph node. You're going to have differentiation. I kind of put this in. You're going to have differentiation of the T cells to particular T cells. And then you're going to have the dendritic cell, for example, interacting with T cells. You get proliferation of T cells. And then the T cells will interact with the B cells, and the B cells will then give you the antibody production. You're going to get, you notice that there's a lot of cells here, right? Truth is, you start out with one, and then it multiplies and multiplies and multiplies. And the whole idea of swollen glands is because you have a lymphoid organ, like a lymph node, and you start out with X number of cells, and they begin just multiplying and multiplying, and they essentially stay here. This is not just an involvement, this is a commitment. They stay together for a good amount of time. And from one cell, you can get 1 million. Okay, it's really, really exciting. Okay, so we said the lymph node or the spleen is where you're going to have antigen meet, and you're going to have antigen meet lymphoid cell. And the reason you have that is because you can't have every square millimeter of the body having all the T cells and B cells doing surveillance. So what happens is you'll have an infection, you'll be draining antigen or pathogen to the lymph node, and then what's going to happen is in the lymph node is where things are going to happen. And that's this recirculation of lymphocytes. Lymphocytes will make their way, okay, through the arterial blood into the lymph node, and then they will then make their way through the through the lymphoid, through the lymphatics, through the lymph and the lymphatics, all the way back into the bloodstream. And what's going to happen is that lymphocytes will be recirculating throughout the body, going from lymph node to lymph node to lymph node. As it shows you here, there's nothing going on in this lymph node, but you still have surveillance. You'll have T and B cells coming in. They don't see anything. They can make their way back into the bloodstream or make their way by daisy chaining to the next lymph node. And here there's something going on. So if any of these lymphocytes are able to recognize any of the pathogens here, you're going to mount a good immune response. And it can go directly in here. So what happens is that this recirculation is a good mechanism by which lymphocytes are able to survey and monitor the entire body. Because all of the infections are going to be occurring in specific spots. Essentially, they drain it, and that's kind of that's really interesting. Receptors of the innate immune system. These are the innate. So they're broadly specific. You have the same receptor on pretty much all the macrophages, and all the neutrophils will have the same one. It's not for NK cell. Okay, and the binding the receptor will promote phagocytosis and other things that I'll show you a little bit later on. These are the receptors. So, for example, you have complement receptors, and we'll discuss complement later. But this complement, it's interesting. This complement receptor binds lipoteichoic acid, which is found on all gram-positive bacteria. It binds to certain nucleic acids, okay, which can actually see bacterial DNA. So we're talking about a receptor here, which is able to see huge numbers, huge variety of different pathogens. N-formal methionine. You remember protein synthesis? It always starts off in methionine. Bacterial protein synthesis starts off at N-formal methionine. So if you have N-formal methionine in a person in your body, that means that there's a bacteria making it. We actually have a receptor that actually tells us, hey, okay, we have a receptor that will recognize that N-formal methionine is being made and that there must be some sort of infection going on. So let's go to the infection. And in fact, this is a chemotactic receptor, and it'll drive the, in this case, a neutrophil to the area of infection. And I'll show you that later on also. Receptors of the adaptive immune system. Remember, I said these are specific for individual molecules on individual pathogens, whether it's annual flu. One thing binding to one won't bind somewhere else. That's it. Okay, next. So this is what antibodies look like. Here's an antibody floating around. Here's an antibody stuck on a B cell. So there's constant regions, and then there's a variable region, okay? And then there's a hypervariable region, which is an antigen binding site. There are billions of different antibodies on billions of different B cells. One type of antibody per B cell, okay? Now, there are different isotypes of antibodies, okay? Different types of antibodies that Carl Hamby is going to speak about. So, for example, IgD will actually be found cell surface associated on the B cell receptor. Your early immune response is going to be IgM, low affinity, okay? Later in the primary immune response or in the secondary immune response, you're going to get IgG. This is how you could tell if a person is on a primary infection or a secondary infection, looking at the whether or not there's going to be any IgM around. Okay, if there's IgM around, you know it's a primary infection, and that's relevant to the lab that we're going to be doing on rubella. Okay, very, very important. You see IgM against rubella in a pregnant woman, big problem. Okay, you see IgG in a pregnant woman, you don't worry about it. Okay, unless it's IgG and IgM. Okay, it just means maybe she was vaccinated, or maybe she had rubella 20 years ago. Okay, IgG is good. Okay, this IgG is better, it's more specific, and has greater affinity. Remember, the secondary immune response, the later immune response, is always better than the early one. In your mucosa, Carl Hamby will discuss with you that IgA is present in your mucosa, and it's not as inflammatory as the IgG, which makes a lot of sense. You don't want huge inflammation inside your GI tract, okay? So that's why it's mostly non-inflammatory, but it is protective. And IgE is, as Carl Hamby will discuss, it's great against parasites and worms, okay? But when you're living in New York, it's not that much of an issue, and you got to worry about allergy. So it's the same antibody class is being repurposed for allergies, not for a pathogen, not for parasites. So now that you have an antibody, what are you going to do with it? Well, an antibody will bind to either a virus or a toxin. Dr. Bakshi was speaking that, hey, there were receptors for toxins or receptors for viruses. This is a toxin. It makes you believe it was a virus. It has to bind to a receptor. The antibodies will bind to the virus or the toxin, prevent it from binding to the receptor, and then this complex will be phagocytized and destroyed. This is great. This is called neutralization. Okay. There's also something called opsonization. It's a big word, all it means is to make something easier to phagocytize, okay? You can have an antibody binding to a pathogen, to a bacteria. Now it's able to be phagocytized much better. Because if you look right about over here, the phagocytes have receptors for antibodies, so that they will bind. Same thing with complement, as we're going to discuss. Complement will bind, the antibodies will bind, complement will be fixed, and then sure enough, there are receptors for both complement and receptors for the antibody, and then this is going to give you even better phagocytosis. Okay, here's just an example of what phagocytosis would look like.
Neutrophils are white blood cells that hunt and kill bacteria. In this spread, a neutrophil is seen in the midst of red blood cells. Staphylococcus aureus bacteria have been added. The small clump of bacteria release a chemoattractant that is sensed by the neutrophil. The neutrophil becomes polarized and starts chasing the bacteria. The bacteria, bounced around by thermal energy, move in a random path, seeming to avoid their predator.
Let's go.
Eventually, the neutrophil catches up with the bacteria and engulfs them by phagocytosis.
Yay. Okay, first of all, as I mentioned every year, at this point, I'm rooting for the staff to get away, but it doesn't, okay? Why did it take so long? Because there was no antibody. If you put antibody on it, boom, it will be over. You'd be able to go back to your cell phones. Okay, it would be really, really good. The other thing is anybody ever, on the west coast of Florida, you can go swimming with manatees. Did anyone go swimming with manatees? You went, right? It looks like the phagocyte, right? It's exciting, you know what I mean? And with a manatee, you could touch it, and you're not supposed to touch it, but if you touch it, you don't have to worry about it engulfing you. You know what I mean? It eats lettuce and stuff like that. Okay, it lets you look like a lettuce. Like a head of lettuce, it's not going to bother you. So I went with my daughter, and it was just so exciting. It reminded me, that's my favorite movie, now because of the manatee stuff. Okay, it's really cool. Okay, now let's get to Dr. Tewari. T cells, T cell receptor, T cells is Tewari cells. Okay, it looks this portion looks just like this. It looks like this is the variable region, and then this is a constant region. T cell receptor is only found on T cells. Okay, it's not soluble. T cell receptor. Okay, what do T cells do? This is a good overview. What happens is, for example, you have CD8 T cells. They see a virus-infected cell. They recognize something on it, and they will kill that virus-infected cell. Antibodies ain't good enough, because if you just have antibodies, the virus will keep making more and more virus, and eventually you're going to get tired of making antibodies. You got to kill the virus-infected cells that are making the more viruses. That's what the T cells do. Now, there's these different cells. This is the CD8, there's CD4. There's different types. Here's a CD4 T cell, and this is effector, and then this is regulation. Okay, you have cell-cell contact and cytokines. Those are soluble mediators of the immune system or inflammation. Okay, this is occurring. Here you have a macrophage that has a bacterium inside of it, and it's not doing a good job killing it. This T cell, this Th1 T cell, will bind to this macrophage and activate it. You get an activated macrophage, and all of a sudden it's going to begin digesting the pathogen, and it's going to be releasing more cytokines. Okay, these T follicular cells, you have a B cell that bound antigen, but you don't want every B cell that binds antigen to start making antibodies. You need T cells to interact with it. This is part of the regulation that Carl Hamby is going to be discussing. Okay, you get this interaction, you get the cytokines being produced, so there's cell-cell interaction, and then there's cytokines and then you can get antibody production. Okay, and this regulation is very, very important. And you could change the immune response. You could change the type of antibody that's being made by playing around with some of these cytokines. That's what allergy shots are. Okay, you're changing the route of immunization. You're making IgG instead of IgE. So if you know this material, you know how to treat and approach diseases. Okay, This is something, I just love the slide because it gives you a good overview of something that Dr. Hamby, Dr. Tewari, and I are trying to get across. The idea of regulation, and this is just an overview. This is from 2008, but I just love this picture. The type of cytokines that you make, whether it's the amount, the sequence, or the combination, will determine the type of T cells. Remember I said T cells come out of the thymus, they're mature, but you don't know what kind they are. If it's CD4, is it a CD4, TH1, TH2? If in the area of an immune response where it's going to see antigen, there's gamma interferon and IL-12 being produced, you're going to have TH1 cells, okay? Oh, by the way, TH1 cells are good against intracellular pathogens. Unfortunately, they're also involved in autoimmunity. That's the flip side. If you have IL-4 around, okay, you make a good immune response, okay, you make that IgE, yeah, I mean, you can promote IgE formation, but this helper cell is good for extracellular parasites, but it also can promote allergy, okay? Same thing here with this Th17 cell. If there's TGF beta around, or should be mostly the something like IL-21 or the or IL-6, you're going to be getting this Th17 cell, and the same thing with the Tregs. So the environment in which a naive T cell encounters an antigen and the molecules around it will determine how it will mature. But here's the scary point, and this is why you get cytokine storm. The next line, okay, not only is the type of cytokines determine the type of T cells, the types of T cells determine the type of cytokines, and there's positive feedback. Look at this, okay? You're making Th1 cells because there's interferon around. But then this Th1 cell is beginning to make more gamma interferon. So it feeds upon itself. It's a positive loop. If it's not well regulated, you're going to get overproduction of the cytokines. Same thing here. Once you start getting IL-4 being produced, okay, here, then you're going to be pushing things into the Th2. That happens in eczema and in allergies, okay? And the same thing here. So the important point is that things have to be regulated, and if you know the regulation, you know how to approach therapeutics. Okay, this is just a very, very quick thing on what Dr. Bakshi was talking about. You know, I was asked to give some lectures to the Th2, to the M2s, the the M3s and the M4s during the beginning of the coronavirus, and we didn't know anything. There were million papers coming out. Okay, you didn't know what was real, and there was garbage being written and published. Okay, because it had COVID on it. You know what I mean? But here's the interesting thing. Okay, I was never an English major, but I do pay attention to words. Okay. The immune response in the literature then was described as pathogenic, awry, misdirected, distracted, aberrant, dysregulated, or confused. Okay, so this is what was going on. And it turns out that too many cytokines, like of these types, were being made. Okay, you're getting more IL-6, GM-CSF, and Dr. Bakshi was mentioning when you're getting more IL-6, you're going to be getting more neutrophils. He was mentioning something about the neutrophil to lymphocyte ratio. You were getting this. You were getting monocytes being made of the CD14, CD16 type that we never saw before. So we were getting a totally screwed up immune response. And instead of the immune response going the way that we would like with viral clearance due to certain host factors, okay, we were getting these guys, and we were getting hyperinflammation. So this goes back to March and April of 2020. Okay, this is what we were seeing, and it was like a totally screwed up immune system. Okay, everything that you learn here, from the regular immune response did not happen with COVID. That's why the pathology was so bad. We're going to finish up on how we go from a very slow immune response to a much faster immune response, from a primary to a secondary reaction. I mentioned that there are billions of different lymphocytes with receptors, so maybe only about 1 out of 10,000 to 1 out of 100,000 would be specific for any pathogen that you're interested in, okay? So what happens is, whether it's a T cell or a B cell, this one will recognize the pathogen. The other 10,000, 20,000 you don't care about. So what's going to happen is it begins to double, right? It's going to be stimulated, it begins to replicate. You get about 3 doublings per day. Okay, 10 doublings is 1,000-fold, right? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,000 plus. Okay, so in 3 1/3 days, you get you get 1,000-fold increase. In 6 2/3 days, you get 1,000,000 of these guys being made. So it takes time, but you're making loads and loads of a specific antibody or a specific T cell. Okay. So this is the reason for the slow primary response, because you're going from 1 to 1,000 to 1,000,000, and it takes time. Okay. What happens then, you make loads of these and you get rid of the infection. Okay. Some of these cells become memory cells. They don't all go away. Remember I said regulation, you want to get rid of this immune response, right? But some of them will stay and they become memory cells. And they stay around. And then what happens is, this is the quantitative difference between the primary and secondary immune response. Instead of having 1 out of 10,000 or 1 out of 100,000, maybe 1 out of 1,000. So now you're walking around you are all walking around with more T and B cells specific for every disease that you've had, okay, for every infection that you've had your whole life. So you are primed, and you're really accommodated yourself to the environment in which you live. You go to a different country, okay, that's what they call Montezuma's revenge, traveler's diarrhea. Why is it traveler's diarrhea? Why aren't the people down, south of the border on the toilet all day? Because their immune system, they're already immune to it. Us going somewhere else, we have zero immunity to it. That's an important point, okay? That's why before you do your travel, before you do your humanitarian trip somewhere, roll up your sleeve and get yourself a vaccine, everything that you need. Very, very important. Let's follow this up. Starting with a few, okay? Bingo, okay? By 14 days, you got tons of these cells, okay? And then your memory phase, you got increased amounts. So these are just cells. Let's take a look at what antibodies will look like. This is in your book, but it was from a while ago. Okay, they don't have this anymore. Whether it's a vaccine or a primary infection, I don't care. Look at this. It takes 12 days to reach the peak. If you didn't have your innate immune system keeping things down, you wouldn't be around 12 days later. Because remember, bacteria, right? Lymphocytes, I said, replicate, every 8 hours. E. coli does it every 20 minutes. Okay, so you don't stand a chance. Okay, so look at this. Okay, 12, it takes 12 days, and you got, let's say, I'm going to make it easy, 10 to the 0. So that's 1 microgram per ml. Okay, in your secondary response, whether it's due to past infection or vaccination, in 2 days, you get it here to 10,000. Okay, so in a very, very short period, okay, you get much, much higher response, okay? And it's a qualitative difference. That's better antibodies. Carl Hamby will talk about that. And it's faster, and there's a quantitative difference. You can get many, many more. Question is, how long will that immune response last? We got this issue with SARS-CoV-2. Coronaviruses cause a cold virus. Many of us get the same cold virus every year, because the immunity we generate doesn't last more than a year, which is kind of crazy, but some viruses have ways to subvert our immune response. Okay, so let's take a break. We'll start at about 10 after or so, or let's start at minutes after. Okay, thanks.